All right, let me try another video solution here. Somebody else asking about this one, and this is good, meaning you're kind of far along on the homework. You're up to 47. However, it is what I'd call a throwback problem. They call it integrated concepts because it takes what we are doing, but also incorporates the stuff that built up to it. And so this would be a good time for me to redraw that picture in in lecture, where if we know the position of it, we can go back and forth with our calculus to get our velocity. We can go back and forth with, again, our calculus to get our acceleration. And again, now with Newton's second law, you can see with net force, because acceleration is net force divided by mass. So if you know one of these, you can go to the other, assuming you have the mass. Now, it's really kind of only a one-way picture, because you got to have the individual forces to add them up to get the net force. But if all you had was the net force, you can't really go back to the individual forces, because there's so many ways that an individual forces, say 2 or 3 individual forces, would add up to one force. And so you don't know when you have the net force if it comes from one force or 2 forces or 3 forces or 4 forces. So you really can't break it down into how many you have and in what direction. And so I have just a kind of a one-way arrowhead there. But again, what we're learning here in this chapter is this segment, and what we've learned in the other chapters is this segment. And I think just by the name of this, the integrated concept, I think they're going to have us go, all the way into this category and start remembering our stuff from the other chapters. Well, let me read it. And so it says a 2.5 kilogram fireworks shell is fired straight up from a mortar and reaches a height of 110 meters. So maybe I have this little mortar in here, and I don't know if you've ever seen these firework stands. Not the stand where you buy fireworks, but where the fireworks are placed. If you ever go to a fireworks show, and they have these little mortars, these little tubes. They're about 2 feet tall. You put the explosive firework down in the bottom, and the explosive firework then gets launched by another explosive. So the explosive then pushes the firework up the tube, the mortar. Then once it leaves the mortar, it continues to rise up, and if I read that right, it's going to go pretty high in the sky, and that's good because this thing's on a little fuse, and so by the time it gets up there, you want it to explode. And so you kind of have 2 explosions. Those of you watching the fireworks only care about the second one. It's like, hey, there it is, exploding in the sky, but those people who are the engineers designing, the pyrotechnic people, they want this first explosion to be just right, so it sends it in the air with the right speed to get the right height and the right timing on the fuse, and you got to have all these pieces fall into place. Of course, you also don't want the first explosion to ignite the firework in the tube. That's where all the safety training comes in, because that would be disastrous, because if you had one explode right here, it would probably explode all the other ones around it, and everybody on the stage who's running it would probably be in the middle of a giant explosion, and it would be just chaotic, and a lot of people get burned, if not worse. Okay, now, putting all that aside here, I can read this that says, neglecting air resistance, and probably a poor assumption, but we will make it for this example. Calculate the shell's velocity when it leaves the mortar. All right, so right here it's going to leave the mortar. And remember, it goes up to a height of 110 feet. All right, this sounds a lot like our one-dimensional kinematics. It's not even a projectile motion because it doesn't have x and y. It just has an acceleration of negative 9.8. We even know its final speed is 0. Up here, this is how high it goes. We're looking for then its initial speed. We don't know time, but we know distance. And so all of that makes me think about equation number 3, I've been calling it, which relates initial velocity, final velocity, acceleration, distance, but doesn't have time in it. Okay, and so as it goes firing up, I would love to find, this is the question, what is that initial speed? Now, I got to be careful with that phrase initial speed, because I'm saying the initial speed as it goes up, so as it is under the influence of the acceleration of gravity. But in the mortar tube itself, you might think of this as a totally different problem in the sense that it would start down here with an initial speed of 0, have a very large acceleration that is not a negative 9.8, and in this short distance of the mortar gets to some final speed, and the final speed coming out of the mortar is the initial speed of the part I'm currently talking about. So don't confuse the two parts of this problem. There's the motion in the mortar itself, but then there is the motion once it leaves the exploding gunpowder from the mortar and then is just under the influence of gravity. So that's why I'm going to say the initial velocity is what I'm looking for. That's the final velocity coming out of the mortar, because at the top of its flight, the final speed is 0. That's what they made it very, very clear that it reaches a height of 110. And so I'm saying that assuming it doesn't explode while it's still going up, it would reach that height and begin to fall, and then maybe on the way down it explodes. Okay, but I'm going to put the 2, and then the acceleration, again, is negative 9.8. At least that's what it is when it's outside of the mortar. And then the height that went is upward, so positive 110. And so you can see all of this, it goes back to chapter 2, one-dimensional motion here. And now you see why it says it's a throwback problem or an integrated problem here. So let me go 2 times, and I'm going to do a positive 9.8 for just a second. You'll see why, 110. And that's the number, technically has a negative in there, but if you imagine moving it to the other side, now it becomes positive. So then if you imagine taking its square root, this would be 46.4 meters per second. And again, we can label this as the beginning speed or the initial speed as it is affected by gravity, or its final speed as it's leaving the mortar. But either way, it's when it's leaving the mortar, whether you want to call it the final of the first part or the initial of the second part. So that answers the question, calculating the shell's velocity when it leaves the mortar. So that's A. So then B is saying the mortar itself is a tube that is 0.45 meters long. Calculate the average acceleration of the shell in the tube as it goes from 0 to the velocity that you just found in A. So their wording helps me, my understanding of we're going to go from here to here. And again, it's about distance, it's about accelerations, it's about velocity, but it's nothing about time. And so that makes me kind of draw my thoughts to kinematics equation number 3, the one that's missing time. And so in this case, if we think about going through the mortar, we would say then it starts with a 0 speed and it ends with a speed of 46.4 meters per second squared. So again, this is the beginning speed as it goes upward, which is also the ending speed for the beginning part. So we're kind of doing the problem, I guess, in reverse, because I'd call part 1 what I'm doing now in B, where it goes up the mortar. And then part 2 of this motion would be now it's under the influence of gravity, and it continues on up for 110 meters. So again, this beginning speed of part 2 is coming from the ending speed in part 1. Now, this is the acceleration in the tube. And it's not 9.8. 9.8 is the acceleration you get if you have only the effect of gravity, not the exploded gunpowder inside this mortar. So this number is huge in order to get this speed in such a short distance of 0.45, I'll put 0.45 meters. And I guess I should put meters per second, and then that unit would be squared. So that I would get acceleration, and I would get it in units of meters per second squared. So, grabbing my calculator, I'll take that number, which is still already in my calculator. I will square it. I will then first divide it by a 2, and then I will divide it by the 0.45, and I will get an acceleration of 2,000, and why don't I say 300, I guess it's going to round to 2,400. And maybe I'll put a line under here for 3 significant figures. How many do they have? 1, 2, 3. 1, 2, 3. Yeah, I think they want 3. So the acceleration is 2,400. I'll put a line under, meaning this 0 is significant, this one is not. 3 significant figures, so 2,400 meters per second squared is the acceleration in the mortar. You can see that's a huge acceleration, but it's going to need that huge acceleration because we're trying to get it to a really high speed in such a short distance, a little bit less than a half a meter. If the object fell from 110 meters, it would take, or it would take gravity to let it fall 110 meters before it got to that speed. So clearly the acceleration has to be pretty big to get to that speed in only a half a meter, because gravity would give it that speed after falling 110 meters. All right, so the mortar itself, calculate the average acceleration. Okay, so again, probably everything I've done truly is so far 2 chapters old. These are all back to chapter 2. But now finally it says, what is the average force on this? And so recognizing that the sum of all the forces, which then, of course, is the net force, has to equal to MA. And so it says here, what is the average force on the mortar shell? Now, I wish they were a little more clear, because if I was doing a free body diagram, I would say that the exploding gunpowder in the mortar is putting a force upward, but I also have a weight downward. And so when they say, what is the average force, I wish they would have been a little more clear. Average force from what? I think they probably mean from the exploding gunpowder. And I would even go far to say that they might mean the net force. However, because the net force would be the force from the exploding gunpowder minus the weight's going to be a small number here compared to the force from the gunpowder. So I think we're probably, and that's why maybe the question's vague, that they could do either one of these. So why don't I do the net force first? Because that would be mass times acceleration. And the mass, they tell us, is 2.5 kilograms. And the acceleration, as we said, was 2,400 meters per second squared. And so the net force is 2.5 times 2,400, and we're looking at a 6,000, and maybe I'll put, for 3 significant figures here, newtons of net force on it. And if we really then wanted to be a little picky, we could say then that the net force plus the weight is the force from the exploding powder. And the weight, remember, is mg, and the net force is 6,000 newtons. So 6,000 newtons plus, and then this is roughly a 25, be 2.5 times, and if it was 10, it would be exactly 25, but it's a little shy of that. So this would be 24.5. So if you put them together, it would be 6024.5. But remember, with three significant figures, you're probably really looking at 6,020. So it does show up in the last digit of the significant figures. So with that in mind, I'm going to go with the idea that the author wanted us to get this force from the exploding gunpowder. And so they didn't just want the net force of 6,000, but they wanted the 6,020. Not completely sure what they want, but you know what? I'm going to take this as an opportunity, and why I still got the recording going, to click on the solutions. Here they are. Let me scroll down to number 57, and maybe I'll just double check. Initial speed 46.4. Okay, good. Acceleration 2,400. Good. They got a net force, and they got 5,990, and they did. They did something interesting. Let's go back and read the question. But they did take just the net force. But then they took the net force and they divided it by its weight. Kind of like saying, how much is the net force greater than the weight? So maybe I read the question wrong. What is the average force on the shell? Express your answer in newtons. Oh, and in the ratio of the weight. Okay, so I just did newtons, and like I said, the author was a little vague whether they wanted to know the net force on it or the force from the exploding gunpowder. And the solution manual did this one. But I really kind of like this one. It does show up here, and I think that might be what they're talking about. But then as a ratio, they're saying take this number, either the 6,000 and divide by the 25, or take the 6,020 and divide by 25. And I'll leave that for you. But then this would tell you how many more times it is than the weight of the object. And that's kind of bit. You get 4 for every 100, and then it would be 60 more. So 60 more, is that... Did I do that right? 6,000 divided by 25 would be 240 times. And this is almost another 25. So this, I'll call it 241, it would round to. So the amount of force on it is over 240 times its weight. And so that's a lot. You as a human wouldn't tolerate that. Your body would fall apart. But these are built a little bit stronger than your body, so they can handle such huge amounts of forces in comparison to their weight. All right, hope that one helps too.